We said that allylic radicals are very stable, and the reason why they are stable because they can undergo resonance. So let's go ahead and draw the resonance structures for this allylic radical. Bonds are going to be broken by a homolytic cleavage. You always start your resonance from the available electron. So one electron is going to go to this bond, and an electron from the double bond is going to come and join this free electron to make a bond. You can either represent it like this, showing the arrow like that, and these two electrons are going to meet and create a double bond now here, or you can go ahead and represent the movement of the electron from the double bond like that. Either one is correct, and you're going to generate a double bond here. So this is going to be your new double bond. Now notice that you still have one electron on this end, and that electron is going to come to the carbon, not to the adjacent carbon, to the carbon that it is on. So you're going to end up having a free radical in there. Going to form a free radical on this carbon. So what I did is I went from a primary allylic to a secondary allylic free radical. Both free radicals are stable, and this one is stable. Although secondary allylic radicals, they are slightly more stable than primary allylic free radicals in there. And there is a possibility that they are going to form slightly faster than the primary allylic radical, but both radicals, they do form because both of them are stable. Not like the primary, this is not like the case of the primary and secondary radicals. Primary radicals, they don't form because they are less stable than secondary radicals. But here, primary allylic and secondary allylic, they are both stable and both are going to form. So these are the two resonance structures for this particular example in here. And the free radical can either be on this allylic carbon or it can be on this allylic carbon. So if I want to go ahead and draw the resonance hybrid in this case, then the double bond is going to be in this region, and free radicals are going to be either on this carbon or they're going to be on this carbon, and both are going to be the adjacent carbons in there. Another example. Now our allylic radical is in a cycle. Okay, you always start your resonance from the radical, and you move the electron towards the radical so that you can create a bond, and the extra bond that is left over, you just move it to the carbon itself. So you're going to end up getting the new position of the double bond over here, and now this carbon is going to be a free radical in there. So I went from a secondary allylic into a tertiary allylic. We said both are going to be very stable radicals. Let's have another structure that has more double bonds and a free radical. The more double bonds you have in your structure, the more resonance structures that you are going to get. So we're going to always start our resonance from the free radical. And it's your choice to pick what side you want your free radical to move. It can move towards this side or it can move towards the other side. It doesn't matter. So I'm just going to go ahead and move it towards this side over here. This means that I am using one electron from the double bond to create a pi bond here. And the leftover electron from this pi bond is going to come and form a free radical on this carbon. So that is going to be our first resonance structure. I'm going to create a double bond in here and a free radical in here. The free radical is hopping from one p orbital to the other. And here I do have a set of p orbitals in there. Every pi bond is 2 p orbitals. And we know that the radical has a p orbital that has one electron. And each of the double bonds have also p orbitals, and each one has an electron. So if we want to draw the p orbitals for these carbons in there, and this is the definition of resonance. Whenever electrons move, electrons need to reside in the p orbital for them to move. So we have a radical in there. All of these are sp2 hybrid carbons, all of them, because they are planar. And since I have a double bond between those two carbons, these double bonds, each one of them is going to end up having a p orbital in there. When the orbitals overlap, they're going to form a pi bond. They overlap because the p orbitals, each one of them have one electron. So notice here that the electrons, they are in the p orbital. So the p orbitals over here, each one of them have one electron. The definition for resonance is that electrons need to hop from one p orbital to the other. So as long as you have a p orbital, then you have a resonance. If you have p orbital and adjacent p orbitals next to it, then you have resonance. On the other hand, if you have one p orbital and then you have an sp3 hybrid carbon, for example, then here you won't have a p orbital, so you will not have resonance. So to have resonance, the p orbitals need to be adjacent to each other. We call this conjugation. So the p orbitals need to be conjugated, means that they need to be close to each other or adjacent to each other. So I'm going to end up having now a free electron over here. I didn't do anything to this double bond, so I'm just going to have the double bond over here. Now it's time to move that double bond. So again, always start from the free radical. Take one electron from this pi bond, and the other electron is going to go towards the adjacent carbon, and you're going to end up getting your second or your third resonance structure over here, having the double bond on the side, the double bond on the side, and now this carbon is going to be a free radical. You keep doing your resonance movement until you get the structure that you start with. So if I continue my resonance over here, then this electron is going to come and bond with this electron, and this is going to be a free radical. So you're going to end up having a different resonance structure in here. And the reason why it is a different resonance structure, because your free radical is on a different carbon. So you're going to end up having now your free radical on this carbon, your double bond is here, and your double bond is here. Notice that I started with a system of two double bonds and a radical. And all my resonance structures have two double bonds and a radical. But the difference is that the radical is moving now. Instead of being on this carbon, it is on this carbon, then it is on this carbon, then it came on this carbon. So it's going to be on every single carbon in there until you reach your starting free radical, or the free radical that you started with. So I'm going to go ahead and move this free radical over here, and I'm going to end up having my fourth resonance structure, having the free radical now here and the double bonds over here. This is going to be my CH3. Keep moving until you get the free radical that you started with. So over here, if I keep moving the free radical, if I move the free radical in here, then I'm going to end up getting the free radical that I started with. So the total number of resonance here, including, whenever you count the total number of resonance structures, include the structure that you started with. So here I'm going to end up having 5 resonance structures. Let's have another example now with benzene. Now, if you have a benzene, benzene is a conjugated system, and that system does have alternating double and sigma bonds. Benzenes are very stable, and all of these double bonds are connected to each other. So here I do have 6 p orbitals on the benzene. Because benzene is very stable, it is not recommended to break any of the double bonds of the benzene. Because if you do this, the system will not be conjugated anymore, and it will not be stable. So this is why, if you have just a benzene and you have a benzylic radical in there, it is not recommended to do resonance and to break any of the double bonds. So do your resonance on the benzylic carbon and any carbons that are adjacent to it. And leave the double bonds of the benzene, do not touch them. You will touch the double bonds of the benzene on one condition, If you have a cycle that is connected to the benzene and that cycle is conjugated as well, then you go ahead and you can move the double bonds of the benzene. Other than that, leave the double bonds of the benzene and don't do any resonance to the double bonds of the benzene. So over here, I'm going to start my resonance towards this carbon is going to be an allylic carbon and the benzylic carbon at the same time. And you're going to end up having one resonance structure in this case. So again, double bonds of the benzene are very stable because they are conjugated. Conjugation means that I do have 6 p orbitals, and these p orbitals, they overlap with each other. So I have an alternation of double single bonds. I don't want to break the electronic cloud of the benzene. So this is why it is not recommended to do any resonance on the benzene unless you have a conjugated system that is directly connected to the benzene. We'll have an example on this as we go. So you have a double bond in here. So you make a double bond in here and a free radical in there. And you're going to end up having 2 resonance structures in this case. You start by moving the double bonds of the benzene if you have a cyclic structure that is next to the benzene, and that cyclic structure in there is conjugated as well. So in this case, I can move the double bonds of the benzene. So here, don't move the double bonds of the benzene. This one over here is conjugated. Why it is conjugated? Because every single carbon over here is an sp2 hybridization. And we said an sp2 hybridization means that I have a p orbital in there. And that p orbital has 1 electron. P orbitals on every single carbon. So if I want to draw the valence bond representation, this is a chapter 1, okay? In organic 1, if you want to go ahead and review that. So if I want to draw the valence bond representation, I am going to end up having a p orbital for every single carbon, because every single carbon in this structure is an sp2 hybridization. And an sp2 hybridization, so every one of those is an sp2 hybridization for all of these carbons and for all of these carbons as well, including this carbon over here. And an sp2 carbon has 3 sp2 sigma bonds, and it does have a p orbital. That p orbital has 1 electron. The p orbital here has 1 electron. These two, they overlap and they make a pi bond. So here, every p orbital has an electron in there. And this is the definition of conjugation you have. So if you have a benzene, and that benzene is connected to a conjugated system, now you can do resonance. And the resonance is hopping of the electrons from one p orbital to the other. So we're going to start our resonance always from the electron in there. Now you're going to end up having a lot of resonance structures because notice how many double bonds you have in there. And we are going to move the free radical across every single carbon in there. So start your resonance structure from the free radical towards this carbon, and this is going to be the first resonance structure here, double bond, free radical in there. Here you go. Whenever you have 2 cycles, finish your resonance structure from the first cycle and then go to the next one. So here I finished my resonance structure from the first cycle, having my free radical on this carbon, and now it's on this carbon. So now I'm going to go to the second cycle. And going to the second cycle, I'm going to move my electron here. I'm going to go move my electron to this carbon, and this electron that is left will be moved to this carbon. So I'm going to end up having my third resonance structure in there. Notice now I moved the double bond of the benzene, because still, even if I move the double bonds of the benzene, I'm still going to end up having a conjugated system. So I can still do that. Here you go. Don't forget your double bonds in there. You need to have the same number of double bonds that you started with. So I'm going to end up having a free radical in there. And now, since your free radical now, to see, you moved your free radical now to this carbon over here. So now we're done from this cycle. That's it. We cannot have the free radical on any other carbon. We started with the free radical here, The free radical now is here, and now the free radical is there. We're done. So now we're going to move the free radical across this cycle. So go ahead and do your fourth resonance structure in there and move the free radical. Here you go. This is going to be one of our resonance structures. Having a double bond here, the free radical is here. And then keep moving your free radical. There you go, forming a free radical there. And every time you generate a new free radical, this means that it's going to be a new resonance structure. This is a cycle of 5-membered rings. Let's draw it as a 5-membered rings in there. So this is a cycle of a 5-membered rings in there. So let's go ahead and draw that as a 5-membered rings. And you're going to end up having a free radical over here. This is a 6-membered rings. This is going to be a free radical. This is going to be a double bond, and I have a double bond in there. If we keep going and generate a free radical on this carbon over here, we already did that in this structure. So now we need to stop. And this structure has 1, 2, 3, 4, and 5 resonance structures. There are more examples in the practice problem. Please practice those.